Audio Jungle. Audio Jungle.
Here we are going to discuss the transformation of stress and of stress. Always remember, for any structural component, for any structural component, we not only have to ensure that structural component is under equilibrium due to external force, but also and every point inside the volume of structure must be in equilibrium and must have stress less than maximum permissible stress, because if stress is what greater than maximum permissible stress, then there will be the chance of the failure of the structural component. This term what I have said here, this statement is very important once you talk about the stress system for any components, for any structural components. Very important, number one. Number two, it is also very important once you take the structural component, so on that structural component it is also very important to know on which plane maximum normal stress will act and on which plane maximum shear stress will act. Because if we would be knowing on which plane normal stress is what maximum, on which plane maximum uh, on which plane maximum shear stress will be acting, based that on that we have to design the, the structural member. Okay, have to design structural component. On that we have to design any component for the aircraft system, or for any system. All right, so this two three terms are very important, and for that reason only we are going to talk here the, the transformation of stress. Because uh, we are going to basically, if you check this normal stress and shear stress, okay, I will show you once I will derive, then automatically understand this. So magnitude of normal stress or magnitude of shear stress completely dependent on the inclination of the plane. That theta, it will be depending on the theta. Once you are changing the theta, once you are changing the inclination of the planes, the magnitude of stress will be changing. Okay, so that calculation from stresses on the plane using method of transformation of stress. That's the reason we are going to transformation to study that stress, to study that normal stress on different planes with different of the plane. They are going to use this method called transformation. Now, if you take the 3D stress system, take the 3D stress system. So how many for 3D stress system I am saying? For 3D stress system, for 3D stress system, how many stresses will be acting? Total, total. If you see total, uh, basically three normal stress and three shear stress. Because we are talking about the 3D stress system. So what are the three normal stresses? Nothing but normal stress on x plane. Obviously, it's a sigma x. Okay, stress on normal stress on y plane will be defined by sigma y, and normal stress z plane. Similarly, shear stress, if you say, so it's nothing but shear stress on xy plane will be definitely it is nothing but tau xy. It is shear stress on yz plane, so obviously it will be tau yz. And if it is zx plane, then shear stress will be tau. So how many uh, stresses will be acting, how many components of the stresses we will have for the 3D stress system? So blindly you have to say it's six: three normal stresses and three shear stresses. Okay, that is the one thing. Now coming to this, if I want to, like, how it is basically, if you talk about the complementary stress, okay, if you talk about the complementary, so that you know very well, tau xy is equal to tau yx. That is called complementary. So few things you need to remember from your basic of strength of material in your graduation. Have done that, and few which is very important, I will mention here one by one. You can. So my point is, if you draw the 3D stress system, like why I said only six stresses will be there, that also there is the reason. Okay. Now I'm just going to draw it x, but y, and it is now for the 3D stress system you are talking thing, but see the 3D stress system important. Concentrate here so you will understand. Now we are talking about the 3D stress. So obviously three plane will exist. That three plane is nothing but x, y, z, like this. And if you say this is nothing but, and how many faces we will have? Obviously six faces for the 3D plane, 3D stress system, or any 3D body. How many faces? Just like a matchbox, total six faces we have. Okay, so can say these are the faces, different faces. This is the one face here. Okay, this is the one face. The just opposite to this, but another face. See the another face, the another face just opposite of it. Similarly, we have a top of this, the one face here, the one face here, and just opposite of this top we have a bottom also. But this one, this is the bottom of opposite to the top. And then one more, which is nothing but front for me and for you also. It will be the front part, which is nothing but, and so this front, this is the front one part, is front one part. And just opposite is what? Opposite to front is nothing but back. Where is the back? Back is what? Here, the back. Now what I'm saying, I'll give the names, it will be more clear. But F, right, to see how many faces. A, this one is the top face, and just opposite to this we have a E, F, top and bottom. Then for me front, for you also it's, but uh, E, H, and just back of it, but C, F, and then third one is nothing but side of this object. If you check what are the sides, it's B, H, and just opposite to this is nothing but AB I have written na, then E F. So 3 plus 3, how many faces? 6 faces we have. Now, if you want to draw the 3D stress system, so listen carefully, you will understand. In the direction of X, one stress will be acting, which is called X. And on the same plane, one shear stress will be acting here in Y direction. What is the plane? It's nothing but X plane. So tau X plane, but in which direction? It's a Y direction, like tau X. On the same plane X, Z direction, we have to draw another stress, which is nothing but tau. What is the plane X? In which direction you are drawing Z? So tau X. The three stresses on one plane. So same you have to draw for the opposite plane also. Like this side it will be, you can say this side it is nothing but sigma X, and just because it is just opposite, just like sigma X is this direction, so just opposite you have to draw here. And similarly Y is just opposite, will be downside. So what you have to write, it's a tau xy, and just opposite to Z here, because this is the opposite plane of this. So it's nothing but tau x. This is the one. This is for two faces I have done. Basically side, nothing but uh, A, B, H and D, C, F, H. For this I have written, I have shown, shown you all the stresses. Now I will use different color. Any plane I can take. Now I am taking this Y. Okay. So obviously in Y direction we'll have a one stress. Y direction we have one stress, which is but sigma Y. And on Y plane we have, obviously on Y plane shear stress will be Y, but which direction? X direction, so tau YX. Similarly here on Y plane only we have to write the shear stress, so it's a tau Y, but in which direction? It's a Z, so it's a tau Y. Okay, this uh, for the top one. Bottom will be just opposite. If I want to draw the bottom side, so it's nothing but the sigma Y here, sigma Y here, this sigma Y. Okay, just this direction will be tau yx. Okay, and nothing but just of this, but tau y. Okay, this is for the bottom, and one is what the front. Bottom I have done, I will show you A, B, C, D. This is the top, this is the top, and bottom both will come. And A, B, H, it is the side. And now this is I'm going to write for the front. What is front? A, D, G, S. Where is A? This is A, D, H. For this I'm just going to write. Where I can write, it is a difficult task for me because space is very less, but I will manage anyhow. I can show you by the answer, which thread I will take. Back I will now see. So for this, I'm just, what is this plane? This is nothing but Z plane. So first in this direction, I will show you sigma Z, nothing but a Z, the Z direction. Then one stress will be in X, but plane is still Z, but shear stress I have to draw in X direction. So tau Z X. And then obviously same plane Z, I'm just writing the shear stress, so it's tau Z, but in which direction? It's Y, so tau Z. This is for the, what I have written here, this is for the front, means ABD, ABGH. And what is for BCEF? BCEF means this. So for BCF I can take this part here. So what is the BCF? That means you have to take sigma Z. This is the sigma Z obviously. And in X direction will be tau zx, and y direction tau zy. So if you check how many stresses, because two times we cannot take, like sigma x we also have here and sigma x we also have, so take one only na, because magnitude wise it is same, only direction will be just opposite. So sigma x we can take, sigma y we can take, and sigma z we can take. But similarly, anyone, I mean, you can take tau yz, this tau yz you take, or this tau yz, because both are same but just opposite direction. So any tau yz you have to take. So I will show you how many stresses sigma x, sigma y has it. Okay, one plane I am taking, positive plane one. Then tau xy you can take this one, or you can take this tau xy. Both are the same, only opposite direction. So I am just taking tau xy. Similarly, I have tau ix also, but I would not say tau xy and tau ix both are different. Both are the same, and it is proved also. It is called complementary stress. Tau xy I can write you here. Tau xy is nothing but tau ix. The complementary stress. Similarly, tau xz we have a tau xz also. So tau xz and tau zx also same by magnitude. Then what is the another? Tau yz and tau yz and tau z. So this three stresses, what I'm saying, if I say tau xy, so I'm talking this tau xy here, this tau xy I'm saying, this tau xy, this one, and this tau xy is equal to tau yx, this two stress I'm talking. So don't think this tau xy and tau yx are just equal, okay, just equal, and this is not just like a tau xy, this tau xy and this tau xy. This tau xy here, this one and this one both are same, I am saying, just opposite plane only. But this tau xy and this tau yx, whatever, at different plane, because this tau xy and this tau yx both are different plane. And here tau xy and this tau xy both are the same plane, just opposite only. Yes or no? Both are the same plane. It's a x plane only, but one is positive x, another is negative x. Just opposite, you can say. So just opposite plane tau xy and tau yx. Similarly, just opposite plane tau xz. Where is tau xz? I can show you. This is the tau xz here, and this tau xz, and somewhere here this tau zx. This tau zx. Similarly, this tau yz, I can tell you this tau yz here. Okay, this tau yz, this tau yz and tau zy. You can take this one, or better if you take this tau yz and this tau zy. Just opposite plane only. See, completely opposite plane. This is called complementary stress. What it is called? Complementary stress. Any of these two, we have to take one. Any of these two, we have to take one. Always remember for the calculation. Okay. Because for the complementary stress, it is clearly proved it will be in magnitude, it will be equal, but in sign, it will be just opposite. Will be just opposite, equal and opposite. That is called complementary stress. You want to draw the this two stresses system. So, what are the complementary stress? If I want to show you complementary stress, you can show by this way, this and this. Similarly, this and so these two stresses are complementary. This two and are the complementary. Comple Always remember, called complementary. Just equal and opposite sign convention. All right. Anyway, so total how many stresses I have shown you? See, this 3 plus 3 6, and this 3 total 9. This is 3, and here 3 plus 3 it's a 6. So total how much? It's a 6 plus 3 9. If somebody asked you just write the 3D stress system. So if you want to write 3D stress system, so you have to say for the 3D stress system, total number of stresses will be 9. Huh? Total number of stresses 9. Have to show by this way. If you want to show by the matrix form, so the 3 by 3, because it's a 3D. Obviously, for the 3D system, you can write uh, sigma x, then you can write tau xy, then you can write tau x z. Similarly, we can write tau y x, then it's nothing but sigma y, right? Tau. Okay. Then another you can write the tau zx, tau zy, and then in few books it is written as sigma xx. That also means z plane and z direction. That also fine. Sigma xx will get the 3 by 3 matrix. So this is nothing but 3D stress system. Okay. But the point is, once you go for the calculation, this is the 3D stress system. There is no doubt about it. Total 9 stresses you will get. But as I told you, complementary stress here. Complementary stress. Complementary. So what are the complementary stresses? You just see nothing but tau xy is equal to tau yx. Nothing but tau xz is equal to tau. Nothing but tau yz is equal to tau. Okay. So these 6 different stresses you have written here. See, tau xy also you have written here, but at the same time tau yx also you have written. So these two are the C complementaries. Similarly, to say tau xz and tau zx, this is also complementary stresses. And at the same time, who go for it also, this tau zy and tau yz, these are also complementary stresses. So, and what about this? This is nothing but diagonal is nothing but clearly it is normal stress. Normal rest are the shear stress. How many shear stresses we have here? Total 6. But again, 6 can be reduced in 3. So this total is what nothing but 6. But using the complementary stress concept, complementary stress equal, equal, but opposite. That is sufficient. I can prove also how it is equal and opposite, but it is not required. So among these 6, we have to choose only 3 for the calculation, because once we know the tau xy, so tau yx automatically we can say this is the value with opposite sign, right? So total number of stresses for the 3D unknown, if I say, then how many unknown we have? Total unknowns are 3 normal stresses and 3 shear stresses. Well, 6 I must. That is my point. Till now, what I tried to explain you, this was the point. So at any point, most general state of stress is represented by these 6 components: sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. As shown you, as I have shown you in this figure. Okay, but in a particular case, not all these components act simultaneously. Depends, like what generally this is for the 3D system, but in few different cases, like if I want to tell you plane strain, you just also need to learn here only. If I say plane stress, so what is the mean of plane stress? Because my job is to reduce the complication, right? Suppose being a, you know if I'm like explaining anything, or if I'm solving also, if I'm solving also, then what is my first priority? To reduce the complication. How I can reduce the complication? See, 3D stress system, how many unknowns? Basically, 9 stresses we have, but in 9 stress we use the concept of complementary stress, and we can reduce it to 3 plus 3, that is 6 stresses. That is also okay, but 6 unknowns are also very difficult task once you go for the calculation. For theory it's okay, but for the calculation point of view, you go for the 6 unknown, also very complicated. Then now what is the technique to reduce this number of unknowns? So one technique is very very clear, that is plane stress, you can say, or you can say plane strain. If you say plane stress, then the meaning of this plane stress is what? Like at least one dimension you are going to reduce. You are going to reduce one dimension. It doesn't mean you can reduce x dimension, you can reduce one dimension, or you can reduce dimension, but at least one dimension you have to reduce. Now if I say for this figure only, for this particular figure only, if I reduce z dimension, if I say z dimension or z axis is what eliminated, so what will be the axis only? Then only we'll have this one, check, this is my x and this is what y. So your plane is what now? Your plane is what now? Only this, because you said z is nothing but eliminated. So my complication is what? Gone. Why? Because for this plane, how many unknown maximum we will have? How many unknown we will have? Very less, because in z direction at least 3 unknown has been gone. So only 3 unknown will be there. In this way, we have a different technique. We can reduce that. Okay, that is the techniques I am saying here. Anyway, so up to here, I think, I believe that up to this it is very clear to everybody. Now, if we go for the next
Yes, sir.
step, yes, we go to next step, and we'll learn what is the plane stress. So if you talk about the plane stress here, so simple. This is very important as well, and for single marks, many times in examination they had asked. So you need to remember this plane stress. So basically, this is the one technique to convert in 3D system, 3D system to 2D plane. Okay, this is the one technique. In short, you need to remember this. So when two faces of cubic elements are free of any stress, free of any stress, when two faces, okay, when two faces, like if I say two faces means maybe x plane, because x plane, how many faces we have? We have a two with two planes. One is positive x, another is negative x. So it is clearly mentioned two faces, you can say, or two faces, you can say, two faces eliminated, we assume that faces eliminated, okay, eliminated, two faces eliminated, or you can say one axis is what eliminated. Meaning is same anyway, because in both word they are using in different books, you should aware with this. We say two faces or one axis is what now? Free of stresses, because we are talking plane stress. So now it is free of stress, free of stress. Okay, now it's very easy now for you to understand. Then if it is possible, if free of stresses, any two faces or one axis is what, suppose free of stresses, then it will be called as the plane stress condition. This is one condition. This is one condition you have to achieve. And how you will achieve this plane stress condition? By eliminating any two face, or by eliminating any one axis. So suppose z axis you have eliminated. So actually two faces you have eliminated, front and back. I will show you z axis. See, this is the z axis. So front. Front means a, what is this? A D G H, A D G H, front, and back also B C E F will not be there. Got my point or not? So that's the point here. You can say if z is what now removed, z is what now removed. So obviously, whatever will be there, it will be on only x. In that way also you can understand. Or another point I can tell you, two faces, if it is said like top and bottom, if you remove the top and bottom also, then uh, obviously z becomes 0. Once you top and bottom you have removed, then z is what gone. Or side also you can say, when z is what gone, then side also it is gone. Like a b e h will not exist because e h and a b will be 0. I hope you understood. So now only one simple plane you will get if you go for the 2D. So in 2D, suppose this is what the 3D plane here. For the 3D plane, suppose, so for plane stress, generally we'll remove z axis because x and y we are very habituated to use that. So generally we'll say okay, z axis is what gone. So only xy plane you may have. Suppose this is, so this is nothing but this z, and this is what x, and this is what y. So if I say it is plane stress, so I will eliminate this z axis. Where is the z axis? Huh? If I say z axis is what eliminated, z axis is what eliminated, we can choose this. We are free to choose any axis we can choose. Generally, we choose z axis. So, what are the plane stress condition? We assume that z axis perpendicular to the face, there is no stress. So, z axis we have to, it means on z axis no stress acting. Means perpendicular face, no stress is what acting on plane of z axis. No stress, no stress acting on the face of z axis. No stress is what acting. If no stress is what acting, then check how many stresses for the related to z we have related to z. Sigma z, that means it will be 0. We have related to z, we have a tau x, that means it will be 0. We also have a tau y z also. Wherever z we will get, that stress will be 0 because we do not have z axis now. So sigma z, tau xz and tau z yz will be 0, and automatically if say tau xz, then tau zx will also be, there is no doubt about it. There is no doubt about it. Tau xz is 0, that means as per complementary stress tau zx also 0. If tau yz is 0, then as per complementary stress tau zy also 0. So these stresses will be 0. These stresses will be 0 when we are considering plane stress. So what are the remaining stress now we have? What are the remaining stress we have? Because this one, you now it is converted, I have to draw the another one also.